Hi everyone, myself Dr. S. Savita, Assistant Professor, Department of Physics, K.S.Rangasamy College of Technology, Trichankodu. Today we will discuss Module 1 of Physics for Civil Engineering, which deals with crystal structure of solids. We will see how the atoms are arranged in solids and why this arrangement is important. Crystal structure form a foundation of material science and engineering because they directly affect the properties of materials. Solids are not just randomly packed particles. Instead, atoms, ions, or molecules are arranged in a very ordered and repetitive way. This regular arrangement is what we call as a crystal structure. The way atoms are arranged which determines important material properties like hardness, strength, conductivity and even melting point also. So by studying crystal structure, we can understand why different materials behave differently. To describe crystal, we use two important concepts that are lattice and unit cell. A lattice is a simply 3D arrangement of points that shows where the atoms are positioned. The unit cell is the smallest repeating block of this lattice that represents the entire crystals. By repeating unit cells in space, the whole structure is completely built. For example, in sodium chloride, the unit cell is cubic with sodium and chlorine atoms are arranged alternatively. Crystals are not all the same. They are classified into 7 different based systems on the edge, length and coaxial angles. For example, in cubic system, it has all sides are equal and all the angles are at 90 degrees, while tetragonal has 2 equal sides and 1 different. Other systems like orthorhombic, monoclinic, triclinic, hexagonal and rhombohedral also exist with different geometric behavior. These crystal systems define overall shape of the unit cell in solids. Now, if you look at how points can be arranged in space, we get what is called as a Bravais lattice. There are 14 types of Bravais lattice grouped under 7 crystal systems. Some common ones are simple cubic. Here the atoms are arranged at corners only, and next one is a body center cubic, we can also call it as BCC. Here the atoms are present at corners as well as center. The best example of BCC is ion, and third one is a FCC, that is face center cubic. Here the atoms are at corners and center of each face. Copper and aluminium is the best example for FCC. These arrangements decide how tightly atoms are packed. To identify and study different planes in a crystal, we use Miller indices. They are written as HKL, where H, K and L are integers. These indices are especially important in X-ray diffraction studies, which are used to find out arrangement of atoms. For example, in cubic crystals, planes like 100, 110 and 111 are very important in physics and material science. Another key factor is how tightly atoms are packed. The coordination numbers tells us how many nearest neighbors surround an atom. The atomic packing factor or APF tell us what fraction of space is actually filled by atoms in a crystal. For example, simple cubic has low efficiency at 52%. That means that packing factor is 52% and remaining 48% is vacant with having a coordination number of 6. While body center cubic structure has a packing factor of 68% with coordination number of 8. And next, the face center and hexagonal close packed structure are the most efficient with a packing factor of 74% and coordination number of 12. So the denser packing usually means stronger and more stable materials. Let's look at some basic examples of real materials and the crystal structure. We know that common salt NaCl has a cubic structure while diamond also has a strong 3D cubic network making it very hard. Graphite on the other hand has a layered hexagonal structure which is why it is soft and used in pencils. Metals like zinc, magnesium form hexagonal close packed structure, and next one is a tin 4 oxide has a structure of tetragonal which gives it special directional and anisotropic properties. So the arrangement of atoms directly leads to different physical properties. Now, why do we study crystal structure? Because they explain so many material properties. Mechanically, they affect hardness, strength, brittleness. In electrical way, that is electrically, they determine whether the material is a conductor, semiconductor or insulator. In thermal way also, they can control heat conduction and expansion. Applications are everywhere from designing metals and alloys to making semiconductor devices like silicon chips and even in nanotechnology and advanced materials. So the crystal structure is the foundation of modern material science. To conclude, crystals are solids where the atoms are arranged in an order repeating manner. Unit cell and lattice are the building blocks of these arrangements. There are 7 crystal systems and 14 Bravais lattice that describe all possible crystal structures. The type of crystal structure determines a material's physical, electrical and mechanical properties. That is why understanding crystal structures is essential for fields like physics, chemistry, material science, and engineering. These questions are based on the material we just went through in the slides. Try to recall the key points before answering. Thank you.